Hey, Chemical Show listeners, this is Victoria. Welcome back to another great episode. I'm doing a quick intro before we get to the main intro for the podcast today. First of all, we're approaching the end of 2023, and it's been a fabulous year. I would love to get your feedback. So you will see in the show notes a link to our listener survey. Please take a couple minutes, fill it out, and let us know how you found the podcast, what you think of the podcast, and what you would like to hear for next year. It will help to define what we're going to do for next year and who we should invite and how we should structure some of our episodes. Jumping into this episode, you'll hear this was a pre-recorded one. I sound a little gruff, and that's because I was battling a cold when I was recording this episode with Joel Shertok. What I really want to point out, though, is what a delightful and interesting conversation it was. Joel has 50 years of experience in the chemical industry. He is a wealth of knowledge. He has learned and forgotten more than most of us know, and he's really an expert in helping companies scale up innovations. Hi, this is Victoria Meyer. Welcome back to the Chemical Show. This week, I am speaking with Joel Shertok, who is the president of Process Industries Consultants. Joel has decades of experience in the chemical industry, helping companies in highly specialized biotechnology, chemical materials, and formulated product environments to implement process improvements and commercialize new manufacturing operations. Joel's seen a lot in his time in the chemical industry, and we're going to be talking about that today. So, Joel, welcome to the Chemical Show.
Thank you very much. I'm happy to be here.
I'm excited to have you here. Joel, what's your origin story? What got you interested in chemicals and what brought you to where you are today?
Well, that's pretty interesting. So it's 1966. I'm a junior in high school. And the question is, what do you want to do when you grow up? The typical coming of age question. And I was a pretty practical guy. I was not going to go to India and join a guru or something like that. So I said, what's a good way of making a living and doing something I enjoy? So I was good in physics. I was good in chemistry. I was good in bio, so there was lots of bandwidth there. I like chemistry a lot. And one day, browsing in the library of my high school, I found a book called So He Wanted to Be a Chemical Engineer. And I said, that looks rather interesting. So I leafed through it and I said, this is very interesting stuff. And then I found out that chemical engineers made a lot more money than chemists. And being a very pragmatic person, I said, chemical engineering it is. And by the time I got to June, July of my junior year, I said, okay, I am going to look for an engineering school and become a chemical engineer. And then as I got more into chemical engineering in engineering school, I said, to do anything really interesting, you've got to get a PhD. So I said, okay, I'm going to get my PhD, and went to Cooper Union for my bachelor's and Princeton for my PhD. And that's how I got to where I is now.
That's awesome. Yeah, I think there's always this trigger moment that somehow gets you into where you are. And as you say, I think then and now, chemical engineers tend to make a little bit more money than chemists. So it's a path with an economic business case.
It's about the only degree where you can get a good job with a bachelor's.
Yeah.
In most cases, you need a master's or a PhD, a bachelor's degree in engineering, and you'll do very well for yourself.
Yeah. Awesome. So you've been in the industry now for, I don't know, I've got to do my math. Is it 40 plus years?
50 years.
Wow, that's crazy. Crazy and awesome all at the same time. So you've seen a lot of change through your career. What do you see as the most striking differences between the chemical industry today versus where it was when you started your career?
About 3 or 4 things. I think the most interesting thing is safety. When I started working for Union Carbide 75, safety was a consideration, but not the consideration. Things went on that today probably get you, if not fired, in serious trouble. In that era, Union Carbide had a big petrochemical plant in South Charleston, West Virginia. It was on an island in the middle of the Kawana River. And the fuming was so bad, people kept their headlights on during the day because you couldn't see otherwise. It was that thick. My first project was working with the cumene phenol plant in Puerto Rico. And we had to have samples of cumene hydroperoxide, which is the raw material, shipped up for analysis. And all they did was they took the vials of cumene hydroperoxide, which is 30% at that point, put it in a little plastic baggie, threw it into a picnic basket, and shipped it to me with some dry ice. No
Wow.
MSDS sheet, no bill of lading, just shove it in, ship it up, and you got it.
Yeah. Yeah. I think that safety aspect is a good one because we take it for granted in some ways now, right? That this is the way that the environmental consciousness, the personal safety, the recognition of hazards, but it's evolved, right? It's evolved tremendously in my career. And I know that it's obviously evolved in your career as well.
MSDS sheets. What's an MSDS sheet? They didn't exist until 1980.
Hmm.
And lockout, tagout procedures in plants didn't exist. What got Union Carbide's attention is a horrible accident that somebody cleaning out a blender, paint blender, in one of the plants, and there was he just turned off the power and he went in to clean it, and the foreman came by and said, "Why is this thing shut off?"
Jeez.
And the guy was instantly killed, obviously, but that was before lockout tagout. And today, my God, you didn't do that, you're gone.
Yeah. Yeah. It's a fundamental these days. Yeah. So what else is different? So you mentioned safety as being maybe the most striking difference between then and now. What else do you see?
I think the emphasis changed too. When I was in the beginning, chemical engineering was petrochemicals. All the chemical companies were involved in petrochemicals in one way, shape, or form. Now, the chemical engineering that I studied is a relic. It's all biomedical engineering, almost all of it. And almost all chemical engineering departments are now chemical and biomedical engineering. If you look at, for instance, I get Princeton's graduate school news every year. And really, none of the graduate students are doing what we consider classic chemical engineering. They're all doing some form of biology, biochem, biomedical. Emphasis has completely changed. And when I studied, everyone had Birstall and Lightfoot, little red book with transport phenomena. That was like the Bible. And I said to my grandson, "Oh, where's your Birstall and Lightfoot?" And he said, "Well, what's that?" Because you're not doing distillation, you're not doing Mayer's transfer anymore. So transport phenomena, as we studied it, doesn't really exist.
Although that's interesting, Joel, because it still does exist. So obviously, I think there's an emphasis now on newer technologies. And I think we're going to talk a little bit later about green chemistries and how that's evolving. Yet, a big part of our chemical industry still relies on some of those traditional technologies, whether it be distillation, catalytic reactions, understanding fluid transfer, understanding heat transfer. That's not necessarily different. I do think that there's obviously more of a focus on green and bio innovations, but some of the core fundamentals aren't going away.
But there will, you still have legacy chemical plants. But I wonder what's going to look like in 10 years when today's graduates are veterans.
Yeah. Interesting. Interesting. I guess time will tell.
Time always tells.
Time will tell. So you started your career obviously working with some major corporations and you've evolved to really maybe more of an innovation and development focus as you go out and you consult with companies across the industry. Tell me maybe a little bit more about what you're doing today and what's the role that you bring in as you participate with these newer, younger companies?
Well, as you pointed out, there's a lot of startups these days. Green tech is really big. It's being funded. So what you'll find now, which is another big change from when I went to school, is a lot of graduate students and a lot of professors, they're going to have to found their own companies. They'll take their PhD thesis and they'll make it a basis of a company. When I went to school, a professor in industry was, outside of doing some consulting work during the summer, it didn't exist. They had no interest. Now, there's a lot of interest in starting your own company.
What's driving that change from your perspective?
A whole bunch of reasons. Universities at some point began to lose their funding. The era of throwing dollars at schools came to an end. And they said, geez, where can we get a cash stream from?
Mm.
And I said, wait a second, we got all these patents that our professors have generated over the years. Let's monetize them. So suddenly industry went into these universities, say, hey, let's see your patent portfolio. Let's see what you got. And since the professors were the experts, naturally, they were engaged by these companies to begin to commercialize their intellectual property. That made professors in industry a lot more acceptable. Basically, broke the glass, so to speak. Now, professors go out and form their own companies, or the graduate students form their own companies, and they become an entity. They go out, they raise their own funds, all the seed rounds, ABC, and it's not that rare. Almost every professor at some point is running a company on the side.
Yeah. And it seems like there's just more money available, more venture capital available to make it feasible.
It comes and it goes, like anything else in the world. I think biotech now is being squeezed. There's not as much money as there was, say, a year ago.
Yeah.
But green tech, plenty of money. Everyone's into green tech. So most of my startups are green tech. They're doing very innovative technology in the green tech area.
Yeah. So when you're working with these companies, and I know you do a lot of work around, it sounds, if anybody can hear the background noise that's going on, there's like a construction project or something going on, and yet there's not anyway. I know that you're going in and you're doing a lot around process improvements and helping companies commercialize operations. What are the biggest challenges that you see that new startup companies are facing in the industry today?
To a certain extent, it's lack of perspective, which makes sense. These are graduate students who have not been in the industry. It's professors who may not be as experienced in industry as somebody like me who's been around. They have a glassware process, and it's good. It's a glassware process, and they make grams of something. And
so say more about what you mean. They have a glassware process.
Okay, so they'll have a process. It'll be beakers and test tubes and Buchner funnels. It's basically a laboratory process using laboratory type instruments. And they'll make 10, 20 grams of processed product X, whatever that happens to be.
Yeah.
Challenge is, and they're aware of that, is how now do I make pounds? And how now do I make hundreds of pounds to begin to make this profitable? And of course, that's the expertise I supply. Is that, okay, things that you can do in a beaker are not things you can do in a stirred reactor. Your heat transfer is going to be much different. Your stirring is going to be much different. You can't use the Buchner funnel to do your solids recovery. But that's fine because there are analogs in the industry that correspond to what the person is doing in glassware. But they're not one-to-one. That's why scale-up is such a challenge and such an interesting thing, is as you scale, your relationships break down. It's highly nonlinear. So going to pounds is one set of challenges. Going to hundreds of pounds is yet another challenge. Each step up, your scale-up equations change.
Yeah. And then getting to millions of pounds, which is where it needs to be commercially viable.
And then you have waste to worry about, and you have heat transfer to worry about. And how am I going to heat this? Am I going to steam? Am I going to use hot oil? It's what you'd expect. And what's more, when you're running a process, you're running it continuously. You're not starting it up and shutting it down. And now you're building up impurities. And you don't see those impurities in glassware because you're not running it long enough. Oh, that could be, and you can be in for a big surprise.
Yeah. So to a certain degree, it's about the understanding the risks that take place at different scales and different parts of the process, and having a much clearer perspective on process risk in the sense of not necessarily hazards, but really truly the risks about how do you actually get your product to be an effective product at scale, at spec, et cetera.
Yeah, and taking into account, you need safety relief now. You need all those things that you don't have to worry about in a chemical lab. Like I was asked to scale up the caprolactone acrylic monomer for the car industry, and the chemist was putting it together in a 100 milliliter flask and so on. And when they said, "Hey, Joel, I got the process, we're set to go." Oh, great! So I ran upstairs, and she described it, and it seemed interesting, not necessarily hard. And I said, okay, that seems like pretty straightforward. What should I watch out for? And he said, oh, I gel batches now and then because you're cross-linking. So I gel batches. And what do you do when you gel a batch? Oh, I throw out the beaker. I said, okay, what's your rate of gelling? 75%. I said,
geez.
no, you can throw out a beaker. I can't throw out a 500-gallon stainless steel reactor. I'm going to have to dig out that cross-link material, which is going to take weeks.
Yeah.
So go back, and when you get the gelling down to 10%, then we talk. 10%,
Yeah, so
10% is a sporting average. You can tolerate that.
yeah.
And she went back to work, and she said, okay, I've got a methodology for suppressing the cross-linking, blah, blah, blah. Great. We did it, made it. Eventually scaled it up into real commercial production, and everything was great. But if I hadn't asked that question about what else should I know, we could have had a really nasty surprise the first batch we made.
Yeah, especially as you start investing more money in bigger equipment and more expensive equipment.
And the other, go on.
No, go ahead.
So the other interesting story I have is we produce caprolactone for the coatings market. And in a certain coatings application, for a big customer, it turned green. It was the most beautiful green you've ever seen in your life. It was a beautifully iridescent Kelly green. It cost you millions if you wanted to do it deliberately. And the customer got away and found a way of getting around the blah, blah, blah. We convinced him this was caprolactone chemistry, couldn't be avoided. The Japanese came in, used a different process, didn't turn green. And the customer said, fix this, or else we're going to lose the business because I can't afford to spend my time working around your mistake. So we had an absolute crash program to stop this coloration. And in the lab, I found that if you treated the caprolactone with 30% hydrogen peroxide, it cured the problem. Now, this is in a 500 milliliter beaker, right?
Yeah.
My boss said, great, we're going to commercialize it. I want you down in Greenville. I want you down in South Charleston tomorrow to commercialize this process. How much? 10,000 gallons. I said, you want me to go 400 mils to 10,000 gallons? He said, absolutely. It absolutely has to get done. We have to save the business. And that's what we did. That was a real calculated risk. The plant manager got everything set up overnight. And I flew in, and they rigged a little pump that pumped hydrogen peroxide in to the bottom of a batch still. And we did it. The yield was horrible, but that wasn't the point. The point was to make a tanker of good stuff.
Yeah, it's interesting, Joel. What do you find is the typical, if there even is a typical duration from getting it to from that lab scale to really commercialization? So I think probably let me change the question a little bit, because I think the time is different, obviously. But what are the key milestones and triggers and indicators that let a chemist or chemical engineer company know that a product and a process is ready to move from the bench to commercialization?
Well, the first thing is, okay, you have a process in a beaker, let's say, a chemical process. The kinetics, the heat generation, the basic purification steps.
Yeah.
If you got those nailed, then you're ready to go into a semi-pilot operation, a 50-gallon reactor, 25-gallon reactor. And that could be 2 to 3 months. It depends how difficult the process is. You're going to run it in a 50-gallon reactor, and you're going 4 or 5 batches. And you say, okay, I think I've got this kind of nailed. I see the heat transfer, I see the kinetics, I see the separation. The question is, okay, are you going to run this batch, or are you going to run it continuous? If you're running continuous, now you have to design a tubular reactor that's going to do the continuous reaction, or a CSTR that's going to do the continuous reaction. Then you have a whole bunch of other problems. You have your heat transfer, you have your mixing issues. Is back diffusion a problem? Are you making byproducts that you didn't realize? And that could take another couple of months to really straighten it out. Then you got all your documentation, which means you have to have all your heat transfer or your mass transfer, everything nailed down. And then you may turn off the plant engineering to commercialize the process. And that could take 6 months.
Yeah. And that sounds really fast, actually.
And that sounds fast.
From what I've seen.
but anywhere from a year to 2 years for a
Yeah.
typical start to finish. And it depends on pressure. If it absolutely
And,
positively gotta, you can get that down to 6 months with the understanding that, hey, you're taking certain risks here.
and that also assumes then that you've got a viable product that has a viable market, and that you understand the market and the use.
Yeah, and that's a marketing issue too. The one thing you don't want to do is spend all this time making something nobody wants. And sometimes that happens. You make a great product and people say, oh, it's nice.
Yeah, I've certainly seen this, right? I think not so much the do people want the product? I mean, I think that's a question, right? Because the world is littered with great ideas that did not have commercial viability because nobody saw the need or the end use, or there was no, or the economics were wrong. But I think sometimes when we talk a little bit about green chemistry and this focused on green and the focus on sustainability, often the ideators, these innovators, the people that are starting this from a lab scale, have a certain view of what the value is and why it's a great idea, which is a gap from what current producers may say or what current customers may say. And I guess the question I have for you is, how do you close that gap? Do you end up playing a role in that gap, or do you say, okay, that's when you need to take it out to the market?
No, my observation, and it is pretty cynical, which is horrible, is people love green until it costs them more money. And then they don't love green so much. I worked for a company, they were a pioneer, an absolute pioneer in green chemistry, long before it was fashionable.
Yeah.
And people walk in, hey, we got green stuff. This is green, it's sustainable. Really, that's wonderful. Oh, it costs a nickel more a pound. No. We developed a floor finish, a really novel floor finish. Didn't contain zinc or calcium. All the curing was done by surfactants. Really a great advance. It gave you 4 times the performance of a standard floor finish, cost twice as much.
Yeah.
You do the calculation, it means you're getting twice the value, right? 4 times the use, twice the cost, twice. And customers could not get their arms around that. They absolutely could not get their arms. They hear twice as expensive, and they
Yeah.
shut down. But you get four
Well,
times the I don't know.
at the end of the day, somebody has to pay for it. And if
There's no
the
such
end
thing as a
user
free
doesn't
lunch.
see the value, because at the end of the day, it's all about what I talk sometimes about the field of dreams, right? There is the field of dreams. If you build
If
it,
you
they will
build it, they will
come.
come. Maybe.
But maybe, but you have to show the value
You
for those
always have to
consumers.
tell because what's in it for you. Like it or not, there's self-interest there. And you've got to articulate to the customer what's in it for you. If you use this product, these are the benefits. And it really can't be touchy-feely stuff. It has to be stuff that they see on the ground that
Right,
they can
right,
justify
right.
it.
So I think this ties back to this whole focus on green chemistry. Um, is there really a green revolution? Yeah, I guess from your perspective, Joel, what's it going to take to really get the green and sustainable technologies to be a real player and a strong player across these industries?
And again, part of my cynicism, but people change their habits only when they're scared. Really. So right now, people aren't scared yet.
Mm.
They're apprehensive. This summer has been a pretty extraordinary summer when you think about it so far. But it's not affecting the average person. It's affecting people at the periphery. People read about it, they understand, say, yeah, things are not good, but no, I'm going to go about my regular business.
Yeah. And so
You
you're
get
talking about kind of the climate change, the temperatures we've
climate
seen this
change
summer,
is
et
really
cetera. Is that what
all
you're
green
referring
chemistry. When
to?
all of a sudden, yeah, when all green chemistry is really, it's we're going to do things without generating CO2 or without generating pollutants and things like that. And people hear that and they like it, but there's not the great incentive yet.
Yeah.
When something really happens to catch their attention, then they say, "Oh, now I understand." When you generate a 180-mile-an-hour hurricane that goes up the East Coast and causes billions of dollars of damage, people will say, "Oh, now I understand. Now I understand." We get a really nasty heat wave, which is not 100 degrees, but 110 degrees. Then people say, "Oh, I understand,"
Mm.
and that will drive it. Which is,
Are
but the good thing is you're getting a foundation now, so you're not going to be starting from scratch.
are people willing to change their behaviors? Because at the end of the day, I think a lot of this is around behavioral change and personal expectations. So I think I am a personal believer that we've seen these hurricanes in the past. This is not the first time we've seen extreme weather events. It's an issue because we've built in places we shouldn't have built.
Absolutely.
We're much more conscious just in the world that we're in. We've got all the data points. We're looking at all the data points rather than anecdotes. And I think part of this is about human behavior and individual behavior.
It all goes back to human behavior. The cumulative effect has to be an individual change in behavior. But a lot of things that we have are hardwired in.
Mm.
People drive cars. America is a car culture, unlike Europe. And people are not going to give up their cars because in some cases you have no choice. Public transportation outside of big cities doesn't really exist. So the question is, okay, you're not going to tell people don't drive because they'll starve or can't get to work. So therefore, what is the best way of driving at the same time preserving the environment? I'm seeing the debate now between electric cars and hydrogen. And that's going to be, in a couple of years, that's going to be that's going to be the big fight. The big fight's not going to be over internal combustion engines. That's settled at this point.
I'm not sure. I don't think it's settled.
Okay, we will see.
Yeah.
But the question will become, okay, are we going to go battery power? Are we going to go hydrogen power?
Yeah.
And right now, it's batteries are winning because it seems more easily attained.
Mm.
It's there. You have Tesla, you have cars. Hydrogen is, people think Hindenburg, oh, it's explosive. It's a different distribution chain. But someone's got to sit down and say, okay, if we have a battery culture, this is our entire system, not just the car, but the mining of the rare earths and the pollution that comes from there. Okay, now you have hydrogen. Now you have to split water into hydrogen oxygen that requires a lot of electricity. Oh, we'll do sustainability. How?
Right.
Where?
I think that's exactly right. I think the challenge is that it's easy to say something else is different, so that EVs or hydrogen or whatever are different and better. And yet they also have some very significant environmental impacts. Absolutely. That I don't think people have come to grips with yet. And I think we're in denial about that. Time will tell.
My take is you can't make A go to B without C. I mean, just anytime you do something, just like people talk about fusion power as this panacea in the future. I'll bet you good money that when they finally develop commercial fusion power, they'll say, "Oh no, we didn't see this coming. There's a side effect. Oh no,
Yeah.
Got it."
Yeah. I guess that's the human nature, right? We have blinders on as to the side effects.
Well, sometimes not even aware. You know, when the internal combustion engine became endemic in the 1920s, people said, no more horse manure. Hooray! Really, the car was an answer to the horse manure problem. All of a sudden, if you read the literature, they did a study in London about 1890, and they said, God, if this keeps up, London will be 10 feet high in horse manure. Just projecting, where things were going to go. So this is a great panacea. Oh, we got a car, no more horses, no more oats, no more this, no more that. Guess what? 50 years later, 60 years later, whoops, there's another whoops.
There's a different consequence.
There's always an oops.
So Joel, let's bring this back to commercialization of new technologies. How could and should companies be identifying those potential impacts? So these maybe unrecognized risks or the side effects. How do you advise companies to identify those?
The best thing they're doing right now is something called a TEA, a technical economic analysis. And they are incredibly detailed. A couple of my startups have gone through that in detail. And it can be an incredible pain to put that together. But it forces you to think. It really forces you to think by having a rigorous methodology saying, okay, you want to go A to B to C. Once sit down, figure out what that's going to entail in terms of energy, in terms of byproducts, in terms of efficiency. And it forces you to confront things that maybe you wouldn't confront if you did the standard chemical engineering study.
Hmm.
So TA is not a bad way of going about it if you got the time and the resources.
Yeah, makes sense. And I think it's probably an appropriate thing to, before you start making the big investments, to understand what those impacts are.
Yeah. The old days of building a plant and saying, oh, no, it's not going to fly anymore.
Yeah. Awesome. Joel, this has been great. What's next? What should we be looking for on the horizon? You've been in the industry for 50 years now. What's your prediction, maybe for the next 10 years or the next 50 years?
I think it's pretty clear we're going to be seeing a convergence of chemical engineering and biology. I think that's going to be the next thing. We've pretty much kicked the standard catalysts as much as we can kick them. So now the next phase is, okay, you can genetically engineer bacteria to make enzymes. You can genetically engineer bacteria to make a whole wonderful bunch of products.
Yeah.
So the old days of taking petrochemicals and throwing them through a catalytic reactor and make something, I think that's going to be the next victim. And the kings of the chemical industry are going to be those schools and those people who can take biology and chemical engineering and put them together.
Yeah.
And I've got several of my stops who are doing just that.
Makes sense. And I think it fits with this green revolution.
It's a conversion of trends, and you can see it. The schools now are not, as I said, not producing the old traditional chemical engineer. They're producing biochemical engineers.
Interesting. All right. We'll see where it takes us next decade and more.
Well, it's like Yogi Berra said, it's difficult to make predictions about the future.
That's right. That's right. The crystal ball is
very
only
cloudy.
So good. It's very cloudy. Absolutely. Joel, thank you for joining us today on the Chemical Show. I've enjoyed our conversation. And thanks everyone for joining us today. Keep listening, keep following, keep sharing, and we will talk to you again soon.
Thank you much.
We've come to the end of today's podcast. We hope you enjoyed your time with us and want to learn more. Simply visit thechemicalshow.com for additional information and helpful resources. Join us again next time here on The Chemical Show with Victoria Meyer.